This resource focuses on actual differentiation using a table of known results. Previous videos then have given a definition and a concise derivation of differentiation from first principles. What we want to do now is give a number of worked examples. So it's normal, once the derivations of key derivatives are understood, to then give the answers directly from a table of known results. So that's what you need. You need a table of known results, and you'll find this in most textbooks, and your staff may even give you one. So what you do not do is derive each case from first principles. You take the table as given. So here's an example. In a table you will find that if y equals a to the x, dy dx is a. If y equals a x to the n, then dy dx is na x to the n minus 1. Another result, if y is sine bx, dy dx is b cos bx. If y is cos bx, dy dx is minus b sine bx. If y is tan bx, dy dx is b sec squared bx. If y is e to the cx, dy dx is c e to the cx. If y is log x, dy dx is 1 over x. If y is sine bx, dy dx is b cosh bx. If y is cosh bx, dy dx is b sine bx. And if y is 1 over sine bx, dy dx is minus b times 1 over sine bx times cot x. Now, this is not complete. I'll write that. This is not complete. The key point here is this is illustrative of the fact that there are a number of known results, and what you need is a table with all the known results so you can call on it as required. So we're going to give some examples showing the use of a table. Example 1 then. Y equals 3x to the 6. We want to differentiate it. So the first thing is to say which formula in the table is relevant. Well, you look in the table and you saw that if y equals ax to the n, then dy dx is na x to the n minus 1. And you look at the formula that you've got here, 3x to the 6, and you say, yeah, that looks like ax to the n, where here a equals 3 and n equals 6. So therefore, dy dx is going to be n, which is 6, times a, which is 3, times x to the n minus 1, which is 5. So you get 18x to the 5. Next example. Y equals 2x plus 4x to the 5 minus x squared. And you'll notice we're implicitly going to use the superposition result, which was given in resource 3. So first, which formula do I want from the table? Well, clearly, all of these terms, all three of them, look like ax to the n, but they look like different ones. So if I take 2x, then that has a equals 2 and n equals 1. So the derivative of 2x is going to give me 2, that's from the a, times n, which is 1, times x to the 0. In other words, just 2. Next, if I look at the 4x to the 5, then I've got a equals 4 and n equals 5. So d dx of 4x to the 5 is going to give me, well, first let's do the n, so I get 5, then times the a, times 4, and then times x to the n minus 1, which is x to the 4. And the final term, the minus x squared, here I've got a equals minus 1 and n equals 2. So d dx of x to the minus 2 is going to be, first start with the n, so that's 2 times minus 1 times x to the 1. And then finally, using the superposition result, we just add them all together. So dy dx must be 2 plus 20x to the 4 minus 2x. Next one then. Y equals 0.2 e to the minus 5t. So again I look in the table and I find I've got this formula. Y equals e to the ct, dy dt equals c e to the ct. So here it's clear that c is going to be minus 5. So d dt of e to the minus 5t is going to be minus 5 e to the minus 5t, but obviously what I've got is d dt of 0.2 e to the minus 5t, so if I add that 0.2 in, I'm going to end up with minus 1 e to the minus 5t. Example 4. So again, this is focusing on the superposition, and you look at the two terms and you see I've got a polynomial term and I've got an exponential term. So for the polynomial term, I use this formula from the table, and for the exponential term, I use this formula. So I can write that d dx of 2x to the minus 4, and here I'm going to do it a bit more quickly. You can see that a is 2 and n is minus 4, so you get minus 4 times 2 times x to the minus 5. So you'll see the n is minus 4, the a is 2, and then minus 1 becomes minus 5. So that gives you minus 8x to the minus 5. What about the exponential term? Well, d dx of 5e to the minus 0.2x, the 5 will carry, and then we use the formula for the derivative. So here c is minus 0.2, so we'll get a minus 0.2 and then an e to the minus 0.2x. And then finally we add those two results together, and so we get dy dx equals minus 8x to the minus 5, and then minus e to the minus 0.2x. Example 5. And here we've got some slightly different formulas. So again, you just look in the table, see what formula you can find. Well, you find the derivative for sine and the derivative for cosine. So now I can write d dz of 0.4 sine 3z is going to be, we'll carry the 0.4 because that's just a constant, and then we multiply by the b, and clearly the b here corresponds to 3, so we get multiplied by 3, and then we get times cos of 3z. And then if we do d dz of minus 0.5 cos of 2z, then we'll carry the minus 0.5 to start with, and then the derivative of cos, we get times and we get minus b, so minus 2, because in this case, if you see the bz term corresponds to the 2 there, so you get times minus 2 and then times sine of 2z. So now if I add those two results together, I get dw dz equals 1.2 cos of 3z and then plus sine of 2z. So final example, example 6, and we've got some different functions here, and it's maybe going to take you a little bit longer, but we should be able to do this one again using the same rules. So there's the derivative for log from the table. The derivative of log x is 1 over x. There's the derivative of sine. There's the derivative for the polynomial, and there's the derivative for the tan. So I'm just going to write these down directly by using the formula. So dy dx equals, so first I'll do the log x, and what you might want to notice, I'll write it here, is that log 3x equals log 3 plus log x. So the log 3 obviously differentiates to 0, and the log x is exactly what we've got in this table. So we get 1 over x. Next, let's look at this term, 4 sine 2x, and you'll see the formula we're looking at is b cosh bx. So we get plus 4, and now the b term is 2, so 4 times 2 times cosh 2x. Next, let's look at this term, minus x to the minus 5, and we're going to use this formula here. So we're going to get a double minus because a is minus 1 and n is minus 5, so multiply those together and you'll get plus 5x to the minus 6. And then finally we look at the 2 tan 5x, and again you've got this formula here, so you're going to get plus 2 times 5 times sec squared of 5x. So this video has demonstrated the differentiation of commonplace functions using a lookup table. In general, it's advisable to have such a table to hand, even though in due course you're likely to remember many of the results.